Hello guys, how is it going? Mike coming back at you here with another video on discrete mathematics. In the previous video, we saw some examples of logic tables, also known as truth tables, and coming up with the possible set of outcomes or truth outcomes for a particular logical form. This video is going to be a continuation of the video previous to that, which was our very first video, where we talked about some of the logical operators that we have out there and what these things do to statements P or Q or R. We're going to continue on that video, and we're going to kick it off by talking about two logical forms or two logical statements being logically equivalent. And the big question is, how do we know if two statements or two forms are logically equivalent? Well, we determine if they're logically equivalent or not through the use of a logic table or a truth table. And the answer is fairly straightforward. Two statements are logically equivalent if and only if the statements have identical truth values for each combination of truth values of the components of each statement or of each form. And that's a little bit wordy, so let me rephrase it like this. In your truth table, you will have columns for each of your two logical statements or your two logical forms. If those two columns for those two forms are identical, and you arrive at their truth values separately, if their two columns are identical, then you have two logically equivalent statements or two logically equivalent forms. Every single entry in every single row has to be the same between those two columns. Consequently, statements are not logically equivalent if, for some combination of truth values of the components, the statements or the forms do not have the same truth values. So if there's even one row where one of your forms is, say, true and the other form is false, then those two logic forms or logic statements are not logically equivalent. In the next video, we are going to see some samples where two logical forms both are logically equivalent, and then we're going to see some examples where we have two logical forms that are not logically equivalent. If two things are logically equivalent, let's give each of these general statements some name. So let's call them capital P and capital Q. If capital P and capital Q are logically equivalent, we write P, and then that's three horizontal bars, all stacked on top of each other. So P, then three horizontal bars on top of each other, and then Q. So here's a couple of examples that we could do. Show that P or Q and Q or P are logically equivalent. Just on the sight of it and just on the sound of it, that just seems like something that it should be. It just sort of seems like common sense, and it is indeed true. The second example here, show that not P or Q and not P or not Q, show that these two things are not logically equivalent. This is the first example that we're going to see inside of our next video. We're going to show that these two things are not logically equivalent. We're now going to move into some fairly basic properties of these logical operators, the not, the or, and the and. If we want to take the negation of a conjunction or a disjunction, how does that change things? What is that logically equivalent to? And the negation of an and statement or an or statement is handled by De Morgan's laws. So we see that if you take the negation of a conjunction, if we take the negation of a disjunction, so we're looking at first one here, well, the not goes into each of your components, P and Q. So we have not P as well as a not Q. But then our disjunction switches to a conjunction. So not P or Q is actually logically equivalent to not P and not Q. So when the not goes into a disjunction, it turns it into a conjunction, and we take the negation of the components P and Q. And the negation of a conjunction works in a similar way. If you negate a conjunction, it turns it into a disjunction, and you're taking the disjunction of not P as well as not Q. So not P and Q is logically equivalent to not P or not Q. We could use truth tables to see that these two things are logically equivalent. There are some cases where we have statements that are either always true or they are always false. And we have special names for these things that are always true or always false. A statement that's always true, regardless of the truth values of the components of that statement or the components of that form, is called a tautology. So what this would be like on our truth, my apologies, what this would look like in our truth table is we have all of our possible combinations of truth values for P and Q, T, T, F, F, T, F, T, F. And in every single one of those rows, if we have a statement that's a tautology, the truth values, that entire column for that statement, will be all trues. A statement that's always false, regardless of the values of, regardless of the truth values of the components of the statement, is called a contradiction. So if we looked at a contradiction on a truth table, no matter the combinations of truth values for, say, P and Q or P, Q, and R, all those 4 combinations or 8 combinations, if our statement is a contradiction, the entire column will be full of F's or falses. And here's just a couple really basic samples, one example for each. P or not P is always a tautology because one of those two things, P or not P, by definition is always going to be true. If P is true, then we're done. If P is false, then not P is true. And anytime you take the disjunction of two things, as long as one of those things is true, which we have here, then the disjunction is going to be true. So P or not P is always true, while P and not P is always going to be a contradiction. For the conjunction to be true, both things have to be true that we are working with, but given P and not P, one of those things is always false. Therefore, you're taking the conjunction of something that's true and something that's false, and that's going to be false. So P and not P is a contradiction. Typically, we give these things special names. We usually represent a tautology by the letter T, and we typically represent a contradiction by the letter C. So here at the end of this video, I have a sort of summary of some logic laws and some logical equivalences. Some of these things are just out there and they're nice to know, not necessarily things that pop up very often and not really things that we'll be working with, but some things are pretty basic and you will want to know. First one is the commutativity of the conjunction or the disjunction. Doesn't matter what order you write things, they're still going to be logically equivalent. So P and Q is equivalent to Q and P, similar with a disjunction. Property number 2, associativity. As long as you are doing two disjunctions or two conjunctions within the same statement, then the order does not matter. You'll still get the same truth value. So P and Q and R is the same thing as P and Q and R, and similar with a disjunction. We said from one of our previous videos that if you have a conjunction and a disjunction happening in the same form, then you have to specify which thing is being done first. It's important because you have one of each. When you have two of the same happening, it does not matter. And that leads nicely into property 3. What happens if you have a conjunction and a disjunction happening within the same thing? What's that logically equivalent to? You can handle that using the distributive property for these logical operators. If we have P and Q or R, this is logically equivalent to P and Q or P and R. So think of it as you're taking the P as well as the conjunction, and you are distributing both things into each of your letters, Q and R, and then you separate those things with the or that you had in there. And similarly, if it's P or Q and R, that's logically equivalent to P or Q and P or R. Number 4, the identity of sorts. If you're going to take the conjunction of a statement P and a tautology, something that's always true, then that's just logically equivalent to P. If you're going to take the disjunction of P and something that's always false, then that's logically equivalent to just P. Number 5, this is actually what we just talked about not too long ago in this video. P or not P is always true. P and not P is always false. 6, the double negative. As you can probably guess, if you have not P and you take the negation of that, so if you have not P, that's the same thing as P. Number 7, the idempotent or idempotent, whichever way you say it, laws. P and P is equivalent to P, as well as that P or P is equivalent to P. 8 says that if you take the disjunction of a statement P and something that's always true, you're going to get the thing that's always true. You're going to get your tautology. If you take the conjunction of P and something that's always false, it's always going to be false, so it's going to be a contradiction. Number 9, the De Morgan's laws that we looked at earlier on in this video. Number 10, the absorption laws. We're going to be taking a look at one of these guys in our next video as well. We're going to be doing a truth table to see that for one of these two things here, these two things are logically equivalent. Absorption, P or P and Q is equivalent to P. Similarly, P and P or Q is equivalent to P. And then 11, the negations of a tautology and a contradiction. If you negate a tautology, you get something that's always false, therefore you get a contradiction. If you negate a contradiction, you get something that's always true, therefore you get a tautology. I would say for the most part, the guys that you'll really have to work with in this course, number 1, number 2, number 3, could potentially work with number 6, and number 9. Those are the 5 most common ones that you'll see being used in this course. Not to say that you don't need to know the other ones, but they show up far, far less often. So this was our video, continuing on our first video. In this one, again, we went through when are two statements logically equivalent? How do you know if they are? You do that by finding the truth table. And then we went through several basic properties of these logical operators. In the next video, we are going to do some sample problems. As I said, we're going to see some examples of two logical forms being logically equivalent, as well as some examples of two logical forms not being logically equivalent. So we're going to get some good practice with that. That's something very important that you'll have to know how to do in this course. Those make very good candidates for test questions. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.